All right, so it looks like there's 5 of you on the call right now, um, and I am recording this, so we'll have the opportunity to. I'll put it up on the course website when this is over, so y'all can review it, and those that couldn't join us can do that later. For those of you on the call, how's everybody doing?
Stressed, you guys see that? I've been trying to do lab 3 all day yesterday.
Oh yeah, really? Okay. So yeah, well we can talk about that. I'm going to talk about a couple of the changes and updates to the course, and where we're going to go. So one thing that I did, I don't know if anybody noticed, that I took all of the PDF of the workbook chapters down. Okay, so I took those down, and what I'm going to do in the future, and we'll talk about this in a second, is assign the homework, and the homework will be in the form of a quiz. So now you should see this homework chapter 10, and you could take the quiz, and they're set up a bit different so that you can take the quiz, and you can actually take the quiz as many times as you want, and you'll see which of the answers that you got wrong, and hopefully that will prompt questions in your mind that you can either go back and review in the book or the video lecture, or you can call me, talk to me. I put my cell number on the announcement sheet. I don't know if everybody. I guess obviously everybody here is getting announcements, but for those that aren't, maybe, and you're just watching this video because you know that I'm going to upload the videos after I'm done, be sure to look through the announcements on Canvas, and you'll see what I'm talking about. So yeah. So today, what we're going to do is I'm going to talk about the test for a little while, see if there's any questions regarding the test, and just note some of the things that I did in grading, and to make sure that as you go back and review the test, you understand what you missed, and then maybe if I made an error grading it in your case. But it should, for the most part, I think I did it right, but I might have messed up in a few cases. Then what I want to do is review chapter 10, and to do that, I have a few examples that I pulled that I pulled up and created myself. And then we'll talk about the homework for chapter 10. And after that, I'm going to present the new material, chapter 11. I don't yet have the new version of the homework up for chapter 11, but I'll get that up later today. So you'll have another new version, and you'll see what it's going to be like when you see chapter 10 today in a second. Okay. All right. So what did I say? So I said I'd start with the test. So I'm going to hit quizzes over here and go to exam 1, and then I'm just going to hit edit, because edit will allow me to show the answers, and you'll be able to follow this along. And I don't think that we'll cover every single one, but I'll kind of get especially things like the matching questions. If you have a question about the matching questions, any of the matching questions, just let me know. And so, we had this pie chart, and the pie chart. Actually, maybe what I'll do is, to keep this a little bit brief, I'll go through some of the I'll go through the questions that I know that I graded significantly differently um, from what they showed up as, because there were a lot of people that maybe misunderstood the question. Okay, so everybody did fairly well on the pie chart, but there was actually some confusion. So I was looking for which category these were. So this does fall into some questions. So this was the healthcare expenditures. Was the Oh no, that's not that one. Europe. So which country was that? I mean, which continent was that? That was Europe. Okay. All right. This one everybody did fairly well on. I do want to note that actually, yeah, I think this one right here, this question 13 was one that could have been maybe determined to be a trick question, maybe. So what is the relative distance measure? So compare data set 3 and data set 4 with respect to the relative distance. So in this one, if you look at data set 3 and data set 4, the points were exactly the same values, but one was multiplied by 10. Let's see if I can pull that up. No, that wasn't it. That's details. Okay. Let's just pull the data up. So these were the two data sets. See how these values here are just multiplied by 10. And so doing so will increase the ratio of the whatever the minimum bounding circle is, or minimum bounding area, will just increase it at the same rate that the rest of everything else is being increased. And so the correct answer for that one was that they would be the same. So, and that's why it's actually a relative measure. And so as a relative measure, if the numerator and the denominator are both changing equally, then they will remain equal as they grow. Okay. All right. Then these sets of questions, I believe I confused many people by saying, identify which of the data sets 6, 7, or 8 is the correct one to answer the following questions, and then answer it. So right here, all I wanted you to do was actually answer the question, but to do so, you needed to find out which data set was the correct data set to use. But I didn't want you to enter anything about the data set, like data set 6, didn't want that in the answer. Okay, I just wanted the answer. So maybe I could change the way I asked that. But for the next time, I give a test like this. But I did try to go back and correct grading. So what I did was, if you answered the correct data set but still didn't give the answer, then I gave you partial credit for the question. If you answered the question, but ideally you answered the question, didn't give. Some people tried to do a combination of both, and if you did give the right answer, regardless of what else you said, I did try to give you full credit. So if you didn't get full credit, then go back and look at that. Okay. All right. So that's having to do with those. Okay. So yeah, there did seem to be a lot of, well, not a lot of confusion, but there did seem to be some confusion with this last part, the hypothesis testing part. But that's really something that we're going to cover fairly well today when we review Chapter 10. Does anybody have, I'm trying to find if there was another, I think there was a question that, I think it was question 30. This, yes, is question 30. Question 30, question 30B, I guess, I didn't actually include an answer. So if you got that one wrong, if you got it right, in other words, if you got 0.05 and I didn't give you full credit for that, please let me know. So I forgot to include an answer there. So whatever you put, you got it wrong. But the correct answer was 0.05. So that's one of the errors that I made in here. I guess I could fix that right now, but it won't fix it for anybody else. It won't fix you because you've already taken the test. But so if you got it wrong and I marked it wrong, and it was auto graded wrong, then you can let me know. Okay. All right. So I'm going to save that. Were there any other questions about the test? Everybody, okay, looks like y'all still there. Okay, well, let's move on then. And to do that, I'm going to open up a sheet. Okay, so here's the GitHub data, and what I'm going to do going forward is, instead of organizing these by weeks, in case there are further disruptions, I'm going to organize the repository going forward by chapters. And so we have a chapter 10, and after class I'll publish chapter 11. So the chapters will have any examples that I go through, as well as the data that you'll need to complete the assignment. Okay, so I'm going to go ahead and open up this project right here. It's not necessary for you to follow along. I recognize that many of you might not have ArcGIS Pro open. So the purpose here is to provide a kind of a real-world example of, if I have a real-world example of using this sort of data that might make even more sense than the way it is organized in the homework assignments. All right, so I have two examples here. One is taken from the book, but it's not exactly like the book. And so we have all of the countries in the world. Okay, there are a few missing. South Sudan wasn't a country that long ago, and so it's a missing link in the data. You can see that there. Then if I turn this is the percentage of females in the labor force. You can see, in North America and Europe it's high. Throughout Africa it's low. It's also lower in some other areas of the world, like South America, than it is in North America, but it's still fairly high. Okay. If I turn this off, you see the Human Development Index. So this is basically a measure of how developed the economy of the country is. And you can see, if you turn those on and off here, there does appear to be a relationship between those two values. So you could ask, do countries that have a high human development index also have a high percent of females in the labor force? Now, we're actually going to get to the point where we're going to look at individual countries or individual observations and the patterns that they establish. But we're not doing that yet. That's later in the course. That's a concept called correlation. Okay, and that's for establishing a direct relationship between the two. If you've noticed so far, I know it's been what 4 weeks, 3 weeks, let's see. It's been some time since we did chapter 10. Okay, but chapter 10 was looking mostly at comparing two different groups. So is this group and this group, are they from the same population or are they not from the same population? That's basically the question that we're answering with chapter 10. So we're trying to find out if two different groups of data come from the same population. Right? So the book points out, and it uses a slightly different data set, so the answers are going to be different, but the book actually groups the world into, I didn't even spell human right here. The world actually groups the world into two different values, a cutoff for human development index, and then looks and sees if the percent of females in the labor force is different between those two groups. Okay? So that's what's contained in this notebook here. Some of these other notebooks I've already shown you when we met 4 weeks ago. They're just simple examples. Going forward, I'm not going to ask you to ever even run a Python notebook. Just interpret the results. And so as a matter of fact, you can actually go to GitHub here, chapter 10, notebooks, and then the notebook I'm about to show you, which is the two sample difference in, I don't know why it doesn't show up there. I'll find that out. It's this two sample difference in proportions test using real data. So if I double click that guy, it should show up. The rest of them show up. I'll find out why. Maybe I didn't push that one right. But you can see that the answers that you need to interpret the results exist right there on the page. So right there on the internet. You don't actually have to run the Python notebook at all. Okay, so you're just reviewing before. If we look back at chapter 10, this test is for looking at two groups of data and determining if those two groups of data are equal or are they not equal. So the null hypothesis is that they're equal. That there's no difference between the two, between this A and B. Okay. So that's the null hypothesis, that these two sets of data are the same. Okay, that they're over. If these represent a sample, the population that they come from are the sample means are equal or very, very similar. Okay, so that's what those two values represent. And so getting back to the test, basically, what we need to be able to do is to interpret the results of this test. Here's the test statistic. Here's the p-value. In order to do that, we need to think first, what was the null hypothesis? That these two were equal. All right? And so the p-value was 0.07, right? Well, in order to find out if that p-value is significant, first we need to decide what our cutoff value is. So it's very, very common to use a 95% confidence level. In other words, we want to be 95%. We want the probability of making an error. In other words, rejecting the null hypothesis when it's in fact true. We want that to be only happen 5% of the time. So that value there, which is 1 minus 0.9, which is 1 minus 0.05, is our cutoff value, sometimes called the alpha value. And so for the rest of this course, once we find out what our hypothesis is, we establish a cutoff value. We're mostly concerned about this p-value and whether or not that exceeds the cutoff value. So in this case, 0.05, we can see really quick whether or not 0.05 is greater than 0.17, and it is, right? But we need to think for a second whether or not we need to consider this to be a two-tailed test or a one-tailed test, because this right now is just the value at the top of the tail. So we either need to double this or half our cutoff value, and that'll be the case almost all the time. Okay, if it's a two-tailed test. If it's a one-tailed test, we don't need to do anything different. Okay, so let's assume right now, if this is a one-tailed test, the p-value is, I said it was less than before. It's greater than. The p-value is greater than 0.05. So what do we need to do if the p-value is greater than the cutoff value? Do we accept or reject the null hypothesis? I think that's probably where a lot of the confusion came on the test. Okay. So you guys can answer in there if you want, but basically, if the p-value is higher than the alpha value, the cutoff value, then we would accept it. In other words, there is not a significant difference between these two values. Okay. So that's that. That's 0.17 is definitely higher than 0.05. Now it would be we would still reject it even if it was a two-tailed test, because we would either double this value or half the 0.05 value to 0.025. So in either case, we would accept that there's no difference between the two measures. Okay. All right. So let's get back to our example here. Okay. This is the example that I want to show you, and that's not okay. That's the two-sample. It's a two-sample difference in mean test using real data. Oh, it is not there. Oh, there it is. Yep. Sorry, it is there. Okay. All right. So here I've read the data into the Jupyter Notebook, and these are the two fields that I'm considering comparing. But rather than compare them directly, which we will cover later, we want to compare whether or not they've got a high HDI, a high human development index, compared with a low human development index. So 1 means high, 2 means low. Okay. let's look at how these look in two different scatter plots. Two different plots. So here's the first one. Oh, looks like I need to rerun it. Again, I'm not going to ask you to run any of the data. Okay. So what I've mapped out here, these are all the countries in the world in a scatter plot. The text is kind of small. Okay, but on the x-axis here is the Human Development Index, and on the y-axis is the percentage of females in the labor force. So in general, as the Human Development Index increases, we have an increase in the percentage of females in the labor force. So that's what that scatter means. Okay. However, there are some countries, see these guys down here, that have, all of these guys right here, they have similar values in terms of their their percentage of females in the labor force, as do other countries in the lower Human Development Index. So in other words, they're more developed, but they're just as often have they just as often have a lower percentage of females in the labor force. Okay, there's not a clear distinction. Okay, so that's how it looks on a scatter plot. Now the other thing I can do is take all of those data and show it in a box plot. So here it is in a box plot. Here are all of the high development index data sets. And here are countries, and here are all the low development index countries. And on this axis is the percentage of females in the labor force. So you can see what this is saying is that, remember what a box plot shows. It shows the median, and then it shows the 25th percentile and close to the very end, and then these are outliers. So when you compare this, let me just rerun this for a second so it shows up. Oh, it won't show up until I close that. So we can't view them simultaneously, unfortunately. But thinking back to the dots that were on there. The values. There were some dots here in the more developed countries, but the bulk of the data was up here. Now in the lower developed countries, all the dots were down below. So this makes sense when you compare the two. I'll close that window. Just making sure I was recording. Okay. All right, so those are the two ways we could visualize the data. All right, now what we're going to do here is run we're going to run a test to compare to see if those two were the same. So first of all, we need to think about what our hypothesis is. Our hypothesis is that sorry, that's the second one. Our hypothesis is that lower developed countries have an equal percentage of females in the labor force as higher developed countries. That's our hypothesis. Okay. And in order to test that, we're going to use the two-sample difference in means test. In other words, we are going to compare those two different values the percentage of females in the labor force for high developed areas versus low developed areas. Let's actually look. And we can see, if we actually just rerun this, we can see that their means are different. Okay, but we're going to say well, what if we had just taken a different sample? Would they actually really be different? Okay. Well, when we run it, we get a p-value. What's this p-value that we get? 1.85. Well, that seems pretty high, but I thought p-values couldn't even get over 1. Okay. Why is this value so high? Remember that this notation, I think we talked about this once before, this notation means that there's actually, we move the decimal place over 27 places and we put a 0 in, and we put zeros in front. So it's really 0.000 27 times. So in fact, that p-value is very, very small. Very, very small p-value. Okay? And so what we're doing here is saying that that p-value is very small. And so we don't even really need to think about what the cutoff is, because what if the cutoff is 0.05, or what if it's half of 0.05? Is that going to be greater than the p-value? Yeah, the answer to the question is yes in that case. And so there's really no debate, or there's really no reason to calculate the cutoff value. But if we did, we would either use 0.05 for a one-tail test, or if we decided that we only wanted to test whether it was different, not that one was greater than the other, we could do a two-tail test, and we'd have to either double this or half the cutoff value. You can do either one. Either way, it will be smaller, and we can reject the null hypothesis. In other words, we could say that the null hypothesis is that that they're equal. So we can say that we're confident that these two sets of data here, anyone with 2 or with 1, are totally different. And so our conclusion is that countries with, there is a significant difference between the percentage of females in the labor force in countries that have a high development index versus a low development index. Okay. Now, the book also points out that there are 2 different types of tests. One test we call a parametric test, and one test we call a non-parametric test. And we are going to learn about, at least for the next few weeks, 2 different versions. And there'll be a slide today where I'll review this. But in general, a non-parametric test shouldn't be used unless the parametric test can't be used. So the parametric test usually has some assumptions that include that the data isn't significantly skewed, doesn't have a lot of skew, that it's fairly normal data. And the second one that's even bigger is that the data the data should be real numbers. So almost all the parametric tests rely on converting your values into ranks. So in other words, here what we could do is say instead of converting the instead of using the raw percent of females in labor force values, we could just use their ranks. Who has the highest? Well, here, this is the way we could do that. So we open the attribute table, we find the percent of females in the labor force. That's this one. It's not named very well, but right there, that country, whatever country it is, San Marino. Okay, San Marino's a little microstate in Europe. That has the highest. So we give San Marino a value of 1. We give Japan a value of 2. Switzerland a value of 3 because it's the third highest percentage of females in the labor force. So you can go down through here. You see most of these are developed countries. Okay, I think all of them so far. Got the United States of America down there, still pretty high. And we go all the way down. Now we start seeing some less developed countries when we get down below. Okay. So that's what the non-parametric test does. Is instead of using the raw values, it just uses the ranks. And the ranks are compared instead of the raw values. All right, close that up. So that's what this one did. Now let's look at the p-value. The p-value isn't much different. Instead of having 27 zeros, I mean, I guess that's fairly significantly different. Instead of having 27 zeros, it's got 23 zeros. So as a percentage, it's different, but still, it's still very, very, very small. Okay. Now, this particular test does allow you to specify whether or not it's two-sided or one-sided. And so, in actuality, I probably should have specified that it wasn't two-sided because we had an idea of what we wanted to do first of all. But even if we said that this was a one-sided test rather than a two-sided test, we would get half this value, which would still be really, really small, okay, on a one-sided test. Or we could just leave it as a two-sided test and remember to half our alpha value. Either way, it's going to be very different. All right. Let's review really quick. Actually, I'm just going to bring up the There were a lot of tests in Chapter 10, but they're basically all different variations of the same concept. Testing two different groups' data. Okay, you're testing two different groups, and you're comparing them to say, are these two samples taken from the same population, or are they not taken from the same population? Okay. So that's what we mean here. Okay, are the samples drawn from two different tests, or alternatively, are they drawn from a single population? In other words, that they are equal. Okay. All right. So there are a few different tests that we talked about. One is the two-sample difference of means test. That's the one that we just went over, this one. So we tested the high development countries and the low development countries to determine if they were significantly different. Okay. So going forward, it's going to be pretty important to understand these charts that are in your book, because these charts will help you. I guess I shouldn't call it a chart. These tables that are in the book, because these tables will help you understand what the purpose of each test is, what the assumptions of those tests are, and then finally what test statistic you're going to get. Okay. Now the test statistic will always involve creating a p-value, and what we're going to do going forward is the software is going to calculate a p-value for you, so you just need to interpret the p-value. Okay. All right. So with the difference of mean test, you're comparing two independent random sample means for difference. What does it mean to be independent? Anybody that's on the call, Did y'all, anybody know what it means when I say 2 independent random sample means? Notice that this is the one that we used to compare the percentage of females in the labor force. What made them independent in this case? Well, basically, it's that they're 2 different groups, and those 2 different groups were measured separately, and we're comparing that same value to each other. In other words, we're comparing the United States, Canada, and Western Europe with Angola, Botswana, Nigeria. We're comparing, those are the 2 different groups. We're comparing those 2 different groups using the same measurement, which is the percentage of females in the labor force. That's what makes them independent. Let's contrast that to, skip ahead a little bit here. Let's contrast that to this. Let's contrast that to the matched pairs test, this one. This is a dependent test. It compares matched pairs from a random sample for difference. What this is doing is comparing 2 different samples of the same group. In other words, it's comparing the United States, maybe percentage of female labor force. Let's compare all the values from 1900 to today. Is there a significant difference in the female labor force when we compare over 2 different time periods? Okay, the observations are the same in the 2 different groups. It's just that it's either a different time period or a different treatment, but it's still the same. So we've got the dependent, or what's called the matched pairs test, versus the independent difference in means test. So those are 2 of the tests that we have. All right. Now, each of these has a non-parametric version that's associated with it. So here is the non-parametric version of the 2 sample difference in means test. So you only would use the non-parametric version if you couldn't if you couldn't answer each of these. Each population is normally distributed. Okay. Well, let's look back at our data here. If you remember when we showed the box plot, we can see that the lower development countries, that looks pretty normally distributed. Okay, we've got a mean and it goes out to a certain point, but the higher development countries, they don't look as normally distributed. There's a big skew toward the lower levels of percent of females in the labor force. So it might be better, it probably is better, to use a the Wilcox rank sum. Okay. Here's the data that they had. So their values were significantly different than the values that I got online. So I don't know where they got their data. Okay, but so that's the difference between the 2. And so if you look at the test statistic here, it's based on the ranks. The W's are calculated from the ranks. And so we just take all of the countries, line them up from highest to lowest, and we compare the ranks. And you don't have to actually calculate the math out. That's what Python did here. It calculated that out. It came up with a test statistic. And it came up with a p-value. That's what it did right here. Okay, significantly different. All right, here is showing some of the math though. Look, we've got the more developed countries. Well, first of all, they only use the top 15 more developed countries. I split it almost in right down the middle. So the average rank of the top 15 countries in terms of top 15 high development index countries, the average rank was 31.57. In the less developed countries, the average rank in terms of their percentage of females in the labor force was 30.41. Okay. So they got a different value. Look at their two-tailed p-value. It's 0.7912. That's a totally different value. That value is really high, right? It's really close to 1. Okay. Let's think for a second, because that is the two-tailed p-value. So we could either half that value for a one-tailed test, or double our, we could either half our alpha value, if our alpha value is 0.05, or double it if we thought it was different. Let's just say we want to say it's different. Okay. Well, then we'd say 0.05, and we divide that by 2, so 0.025 is our cutoff value. Is 0.025 less than or greater than the p-value? It's much less than the p-value. The p-value is much higher than the cutoff value. And so in using this data, we would have to accept our null hypothesis and say that there is not a significant difference between these two values. Okay. So that's totally different than the numbers that I used here. See how this is a really, really small value? This is a really large value. This will result in accepting the null hypothesis, and this will result in rejecting the null hypothesis. But in each case, the null hypothesis was the same, that the high developed countries have a similar percentage of females working than the low development countries. So in this case, we said, yeah, they do. In this case, we said, no, they don't. Okay. All right, so that covers the two sample tests where we're only looking at the values themselves. What if we've got a proportion to cover? Well, that's this one. So there's two different proportion tests as well. There's a parametric proportion test, and there's a non-parametric proportions test. So here's the table for the parametric proportion test. Compare two independent random samples for difference of proportions. And then I don't have the slide for the other one, but I've got it up here as a Python notebook. But so we've got our difference in proportions, and we've got a parametric and a non-parametric version. So in order to show this as an example, what I did was I randomly sampled a bunch of points from all of South Mississippi. So I have every single county in South Mississippi. I define that as basically this area that you can see here. And in each of those areas, I used some data to determine if the land cover changed between those two time periods. So here, the land cover went from 43 to 43. So it didn't change. That means the change is 0. Here, the land cover went from 42 to 71. I'm not exactly sure what all the land cover codes are, but they could represent going from forest to wetland, let's say. We got a change value of 1. Right? So this Python notebook actually talks about, or actually shows the test. Okay, So the test here is, the first thing I did was take the data and I organized it by county and summed up. This is the not changed, this column, not changed. This is the change. So in other words, change, no change. Okay. So you could see in what most of us are either in Forest or Lamar County, if we're in Hattiesburg, or if we're on the coast, we're probably in Hancock, Harrison, and Jackson. You could see, for example, Jackson had 63 points where there was not any change, and 7 where there was change. Okay. Whereas Harrison had 49 no change and 21 changes. So that's a lot more. Okay. So what if we want to ask the difference, or we want to ask if those two are different? Or what I actually posed here, I want to find out if Harrison is different than Lamar County in terms of the land cover change between 2001 and 2016. Okay. Both Lamar County and Harrison County are experienced some growth in those time periods, but did that influence the proportion of land cover change? Well, if we want to answer that question, we do it by running this test right here, the difference in proportions test. Okay. So it has to be organized by yes, no. So we have change, no change. So when we run that, we're going to get a value, and it is a z-value. Okay. So looking at the z-value, we can see really quickly that the z-value, and we know the z-values are measured in standard deviations away from the mean. So we can see that we're still less than 1 standard deviation away from the mean here, which probably means that our test statistic is going, our p-value is going to be pretty high, relatively speaking. Okay. So this is true with the z-value, but with some of the other test statistics that we're going to see, it's not always going to be a z-value. So that's why this isn't as important going forward as this. The two-tailed p-value there is 0.337. Okay. So should we accept or reject the null hypothesis? Well, first of all, what is the null hypothesis? Well, the null hypothesis is that the land cover change between Lamar County and Harrison County between 2001 and 2016 is not significantly different. There's no significant difference in the proportion of land cover change between Lamar and Harrison County. Well, we got a pretty high p-value. In fact, it's going to be much higher than either 0.05 or 0.025 if we half it. Either way, it's going to be higher. Okay. So what do? Do we reject or accept the null hypothesis? Well, we would accept the null hypothesis that they're the same, that they're similar. Okay. Lamar and Harrison County don't have significantly different land cover change value proportion. The proportion of land cover change is not significantly different between those two. Okay, because this is high. Now let's compare two counties that might have different value. Jackson County has hardly any changes. Okay, and Jackson County, for those of you who don't know, this is Jackson County. By the way, the colors actually represent the percentage of land cover change. So Jackson County had a lot less than anybody else. Why? I don't know. It does seem like, if we turn this off, it does seem like it's fairly, most of the county is fairly rural. Of course, that's true of a lot of these places, but maybe there wasn't a lot of change going on in those areas. Okay, so let's look. Let's compare neighbors here. Oops. Let's compare those two neighbors. Lamar and Harrison. So instead of Lamar, we'll compare Jackson to Harrison and run it. It's going to make me run this one too because I hadn't run it yet. And again, you won't have to run any of these. Okay, so now we compared Jackson to Harrison. Okay. Now look at the value. The value of the test statistics, 0.875. Remember that since this is a z-value, that's in standard deviations. So it's very unusual. It's way far out on, it's 8 standard deviations away from the mean using standard normal. So the p-value is going to be really small. Now it's not like it was here where it's minuscule, literally 23 zeros out in front of it, but it is fairly small. Okay, 0.003. Right. Now that's actually getting close, but it's still just small enough that it doesn't matter whether we were going to do a two-tailed test or a one-tailed test. And it doesn't matter whether we take 0.05 or 0.025. Both of those values, those cutoff values, are bigger than this value, right? They're both bigger than that value. And so if we take that value and it's less than whatever cutoff value we're going to come up with, unless we went out further, like if we went out to the 99% confidence interval, then it would be 0.01, be less than that. The p-value would still be less than 0.01, but would it be less than 0.005? Yes, it still would. Okay, so even if we did this at the 99% confidence level, this p-value would be less than our cutoff value. Okay. So it's very it's very, very small. It's less than. So in any time the p-value is less than the cutoff value, we can reject the null hypothesis. And so what we're saying is that Jackson and Harrison do have significantly different values in terms of their land cover change. So the value for Jackson and Harrison is different. So in other words, there's a different amount of land cover change. And we decided even if it was two-tailed, we could reject the null hypothesis. So we could say that Jackson County had less change than Harrison County. There's significantly less change in Jackson than there is in Harrison. Okay. So we could safely say that. So we can compare any two counties this way. We could compare Perry to Jackson. Okay, Perry to Jackson. Yeah, that's back to where the value's high. Okay, test statistic not as high as it was before when we were comparing Lamar and Harrison, but it is 1.5 standard deviations away, which gives us a p-value of 0.21, which is still going to be greater than 0.05 or half of 0.05. So what does that tell us? Well, there's not a significant difference between Jackson and Perry. So if you look at the map here, Jackson and Perry here. Okay, they look like they're different colors, but based on our sample, we can't tell if there's a significant difference. If we want to go get more data, we could get a bigger sample, and perhaps there might be a significant difference. But based on our data, there's nothing to conclude that Perry and Jackson have a significantly different land cover change proportion. Although we were close to meeting the cutoff, closer to meeting the cutoff value than we were when we compared Lamar and Hancock County. Okay. Now, just as a preview here, we can actually use the same method, and this is only for this test. It's not the two-sample test. We can use the same method to compare 3 counties. Okay. So here we're saying, is there a significant difference between the proportion of all 3 of these counties, or are they the same? And notice the p-value got even lower now if we concluded Jackson, Perry, Lamar. In fact, we could even leave out, just leave out all of this and say Jackson, Perry, Lamar, everything. Are they all equal or are they different? Now, of course, we're going to get a value that is of course, we're not going to be able to see the individual comparisons anymore. This is asking us, are Forrest, George, Green, Hancock, Harrison, Jackson, Lamar, are they significantly different from each other when considered as a very large group? Well, look at the result here. The result here is that the p-value is still relatively high. Okay, it's 0.011. It's getting close. Like maybe at the 90% confidence interval, we'd be close to rejecting the null hypothesis, but we still can't. And so, if we're going to consider the question, is there a significant difference between the land cover change values for all of the counties in South Mississippi? We'd have to say no, based on this information. Okay. Now you might be asking, why is it that the question is no here? Well, we'll get into that a little bit more. That's actually not this week, but next week, chapter 12. But we're going to start getting into it today. Today we're going to look at what if we had more than two different samples. In other words, what if we divided the world up into three categories: high, middle, and low, and looked at the percentage of female labor force in the high developed, the middle developed, and the low developed. So that's what we're going to do today. Okay. All right. Hopefully we've had enough practice with doing that, because what I want you to be able to do is do this yourself with the homework. It looks like it didn't download my updates, because I have two other notebooks that will help you with the homework. So let me hold on here just a second. I'm gonna close this. I'm not going to save any of the changes because we just looked that up. Okay. So hold up here. Okay, just a second here. Let me make sure that I uploaded it on my other. Okay, it is up on GitHub, but I don't know why it hasn't transferred over here. Yeah, so I'll solve that problem in a bit, but it's up on GitHub, so we can actually look at the homework and answer the questions by looking directly at the GitHub answers. Okay, so let's practice this, because this is what you're going to have to do for your homework. So we're going to review. So now, if we look at the homework here, I'm going to bring that up. If we go to quizzes, actually, you can get to it. I think the best way to get to it probably is to look at the modules and then go down to week 6 here. And you'll see that there's a homework chapter 10. Canvas calls anything like this a quiz, but this is basically your homework, okay? So I'm going to hit preview here, and that way I'll see what you see when you go to test it, okay? So this is the test. I mean, this is the question that was originally in the homework. I modified it a little bit, changed the data up. But now the data can be found here. I'm going to make it so that all the data will be up on GitHub, and I've separated out by chapter so that you can go specifically to the spreadsheets that you need, okay? Rather than saying which spreadsheet is it that I need to find. So this says the housing collapse of 2007 and 2008 serious impacts. That's the same as it was before on the U.S. economy. People were concerned. Even after many years, the housing prices didn't recover. So basically, what we want to determine is, was there a recovery? Are the home values in 2005 significantly different than 2010? So I'm going to open up this spreadsheet. If you just click on it, it'll open up the spreadsheet, and you'll see the spreadsheet. So here is the spreadsheet, and we're just looking at these two. Okay, I am going to post a quiz for this one, but right now the only spreadsheet you're using in this is this one right here. The sale prices for new homes in Lamar County are here, and the sale prices for new homes in Lamar County for 2010 are here. Okay, so you've got two sets of data. Now, notice that there are 41 homes. Do these represent the same 41 homes? It's the first question to ask yourself. Is it reasonable to think that the same 41 homes sold in 2005 versus 2010? No, it's not. This is a random sample of all of the homes that sold in 2005, and this is a random sample of all of the homes that sold in 2010. Okay. So this is not a matched pair question. This is just like the question that we did with the countries. Okay. So instead of the higher developed countries and the lower developed countries, we're doing sale prices in 2005 versus sale prices in 2010. Okay. That's what we're doing. So that's how you answer that question. Okay. So you need to state the null and the alternative hypotheses. So I'm not going to answer these for you. Okay. So based on what I've talked about today and reading back in the book, you need to answer which one of these is the null hypothesis and which one is the alternative hypothesis. I think, it's going to tell you whether you're wrong or not, but I think it would be best to do your best. You'll learn more out of it if you try to answer it correctly, answer it, and then correct the things where you got wrong. Okay, so find out what the null and the alternative hypotheses are. Okay. All right. Now, here I said in assessing the recovery of the county, compare the two random samples. So since it's a recovery that we're testing for, in other words, in 2005, the values should be either equal or higher than they are in, the values in 2005 should be higher than they are in 2010 if there isn't a recovery. If there's a recovery, they should be equal. 2010 should be equal or greater. Like, we don't really care if 2010 values are greater, right? Like, if they're greater, then a recovery happened. But if they're lower, then a recovery didn't happen. Because we assume that house prices go up over time, right? So think about that when you state the alternative hypotheses. So 2010 may not, it only matters if it's lower. So think about that when you do that alternative hypothesis, state the hypothesis there. Okay. So question 2 here. This is where from now on, I think it's very valuable to be able to calculate mean, standard deviations, and to know what those values are. But a lot of these test statistics can be calculated in software just fine. You just need to be able to interpret the results. And it's nice to be able to understand how to use the software. And so I do have those as examples, but you don't have to be able to code it up in Python to be able to answer the question. But you'll see it's pretty easy. So if I go to GitHub right here, you'll see, oh yeah, I hit refresh there. I guess it took a little while. Okay, you'll see that I have a Python notebook for both part 1 and part 2 here. So this is saying, oops, sorry, it's not. What this is saying is, all the following questions can be answered by looking at the Python notebook called Chapter 10 Homework 1, located on GitHub. If you have trouble finding this table, please let me know. You don't have to rerun the Python to find the answers. So you go here, you hit Python Homework 1, and it'll load, and it'll actually show you how I got the data from Excel. It's the same Excel spreadsheet as this. I'm just reading it into Python. And so we have all the data here. This is just the index. We have all the data, and all the data is just 2 columns of data. All right? And so the code here is really simple. All I'm doing is I'm getting 2 groups of data. And how I get the groups of data depends. Because with the countries, it was different, right? So here, this column represents group 1, and this column represents group 2. But, oh, I already closed it down. Let me open it back up. I'm just going to open this back up because I'm going to show you how the data was different. And so it made a slight difference into how how it was coded. So if I go here, you'll see if I look at the data, the groups are a column called, well, actually they're not in there. They're in the notebook. Difference in means test with real data is what I need. There it is. Okay. Okay, you'll see that it was all this is the column I want to compare. It's all just one column, and the groups are assigned by an identifier, 2, 2, 1, 1. So the groups are ordered differently, and so I had to manipulate the data differently. But here, if the data are in 2 different columns, then it's easy to just say, okay, I want this column as group A and this column as group B. Okay, so here I'm going to, I printed out the mean and the standard deviation for both 2005 and 2010. and then I printed out the results of the t-test that I did. And I did an independent t-test. Why did I do an independent t-test? Because these aren't matched pairs. In other words, this isn't the same exact house being sold in time. What if I actually had an appraiser come and appraise the same exact house over time? Then I could do a matched pairs test. And the code would be slightly different. It would be using this code where it said t-test underscore rel. So related. That's what that means. Okay. So I could run that too. No, I can't run it because this is on. So you don't actually have to run this. You have all the information you need here to answer the question. Okay? Did the mean get higher or lower or stay about the same? Well, staying about the same is kind of a judgment call, but let's see. We've got 171,000 versus 160,000. So it went down, right? But is that a significant difference, being that we only had 40 houses that we sampled? Okay, especially since they aren't the same houses. You know, any sample of 40 houses could be different than another sample of 40 houses. So does it tell us if the proportion is, if the the overall mean is different? So you use these values. Okay, I'm going to ask you for some of these values here, and you can just copy and paste them from GitHub. What's the mean selling price of homes in 2005 to the nearest dollar? So 1.18 cents. What's the mean sale price of homes? What's the test statistic? In this case, it's a t-value that you're getting. Okay. I'll give you a hint. That's this value right here. It actually says it's the test statistic. Okay. I mean, remember that is like the z-value. It's in standard deviations from the mean, and so it's just that the t-distribution is slightly different. So there's a different amount under the curve. So they're just not, they're just not those numbers that you might have memorized. The 1.96, 1.65. Okay, so you put all those values in here, and then I ask the questions. Okay, so these are more thinking questions, but I made a multiple choice, so it'll be a little bit easier. These questions can't be answered by simply looking at the Python output, but they require some thinking. So you can refer back to the book, you can refer to the video, you can even ask me questions if you don't understand. So is it a one-tailed or two-tailed test? So you have to answer. Okay. With this knowledge at the 95% confidence interval, what should the alpha cutoff be? Okay. Should it be one of these values? Okay. It looks like I accidentally put in 2 blank values. It's not one of those anyway, so I'll try to go update that. Okay, and then should you reject or accept the null hypothesis? That's where you can you can specify whether you should reject or accept the null hypothesis based on this p-value. Okay. All right, and then finally, you need to evaluate which of those statements is the best conclusion regarding Lamar County housing values between 2005 and 2010. Okay. So which of these is the right answer? Think about that and answer the question. Right. This next one, it's the same type of question, but we're looking at difference in proportions. Okay. So the questions are actually the same exact questions. Okay. State the null and alternative hypothesis. This time you're looking at proportion instead of means, so you're going to find those, and those will be on the GitHub chapter 2 here. Okay. And you can see here there wasn't a table. I didn't read any of this data in. I just punched it in to here. Okay. So 69 out of 95 and 59 out of 105. That's what we said here. Okay. So we said here. 95. So 69 out of 95 or 59 out of 105. Did do that right? Yeah, 69 out of 95. Okay. So you don't even need Python to calculate these values, but I did put them in the Python code. I put the code there to do that. Okay. So what's the test statistic? That is on the Python. What's the p-value? That is on the p-value. Okay. All right, and remember, just like the example I did with the land cover change in Mississippi, that result is always two-tailed. That's the way it comes out, and so remember to double the p-value. Double the p-value, or half the cutoff. Okay. In order to get that. Well, in this case, you have to do that. Yeah. Remember to double the p-value. All right. It may or may not matter. Just let you know. Just look at the numbers and you'll see whether or not it matters. Okay. And then finally, you have to come up with a conclusion on that. Okay. All right. So that is that's how you answer those questions. All right. And the chapter 11 will be really similar. Okay. It'll be there'll be a quiz associated with it, and I'll have already run the Python code that you can refer to. But all the Python code is doing is data wrangling, because almost all of these just expect a bunch of numbers organized in a certain way. And so you organize the numbers the right way, then Python can calculate the test statistics that it needs to answer the question, okay, and give you the p-value. So you just need to know which test to run, and then there'll be lots of software out there for you to actually run and answer these questions. But you do need to know how to interpret the results. Okay. All right, so I'm going to close that. Any questions about homework there? Whoops. We'll answer a question, asking a question. That's what I need, right there.
I'll make a comment.
Okay.
I like this because we'll get feedback right away on it.
Right. That's good. Yeah, you'll get feedback right away. It won't actually show you the right answer until the quiz is due. But if you get like 5 wrong answers or something, then contact me, and we'll talk about why you're having a confusion there. See what I'm saying? So that way you keep hunting for the right answer. Now some of them, obviously the multiple choice ones, you can just get the right answer by answering it multiple times, but that's not the purpose of doing it. Okay. All right, so let's talk about today's material. And luckily, today's material is pretty short. There's not a whole lot of new material presented. And there's actually a lot less tests than there was even in Chapter 10. So in Chapter 10, one way to think about it is there's all 2 sample tests, but there was independent match pairs, and then there was the non-parametric versions, which was the rank sum tests, and then there was the difference in proportion and the non-parametric version of that one, which is the Mann-Whitney test. So there was basically, depending on the way you look at it, 5 or 6 different tests that we talked about here. Well, in Chapter 11, there's only 2 different tests that we're talking about. And not only that, they're just building off of the matched pair concept. Okay, so Chapter 11 is this 3 or more sample tests. So in other words, instead of just, I gave you a little preview of this already. In other words, instead of just looking at group A and group B and comparing, are these two groups from the same sample, are they significantly different? We're now looking at group A, B, C, ... N. Like we could have multiple groups. We could have 3 groups, 4 groups, 5 groups, 6 groups, 7 groups, all the way up to, theoretically infinity number of groups. So that's what we're doing today. Talking about the tests that compare 3 or more groups or samples. And they all have to be samples, or we're assuming that they're all samples. Okay. So the name of this test is called an analysis of variance test, or ANOVA. And the ANOVA test is the parametric version, and so it assumes that each of the samples comes from a normally distributed population. And actually the null hypothesis is that they all come from the same population. They're all really the same. There's not a separate group. There's not separate groups. There's just one group. Okay. So all the data also has to be interval ratio. In other words, we have to be measuring something that is a real number that represents a real value, like with the like with the example that we just did. Why can't I think of it? Oh, money. It's house prices. So if we had 2005, 2010, and 2015, we would use the ANOVA instead of using the 2-sample test that we did before. So this is the same test that we just talked about, but now we're adding, well, what if there's a third and a fourth group to test? Okay. So the underlying, what makes the model work, or what makes the test work, is that we assume that the variance in all of the group populations are equal. And if we find out that they aren't, then we'll get a value. We'll find out that they're significantly different. We'll get a really small p-value, and we'll reject the null hypothesis. We'll say that they're different groups. All right, the non-parametric version of this test is called the Kruskal-Wallis test, and it, similarly to the other 2 non-parametric tests, the Mann-Whitney and the Wilcox rank sum, similar to those, it basically takes the original interval ratio data and converts those to ranks. Now, you can actually, if you already have ranks, you can use the Kruskal-Wallis test in order to, you can use the Kruskal-Wallis test directly. So you either have ranks or your data can be converted to ranks. Now most software packages will do the conversion for you. You don't actually have to rank them, but it would be data crunching, but you could do it. You just line them all up and you assign the first one 1, the second one 2. Now sometimes you might have two observations that have the exact same value. Like let's say we had 2 countries that had 69% of the women in the labor force, and we ranked them all. Well, you have to consider each one of those values as a tie, and they each get the same rank value. But when you move on to the next one, let's say they were the 5th and 6th, well then you'd give them each a 5, but the next one you'd give it a 7. Okay, and again, the software takes care of that, but that is what you have to do if you were going to calculate this out manually. Okay. Similarly, like if I said, well, if 3 people got 100, and that was the highest score on the test, 3 people got a 100 on the test, and the next person got a 98, I would tell that person, they got the fourth highest grade in the class, not the highest grade, not the second highest grade in the class. So that's what I mean there. Okay, so that's all right. So it's ordinal data or downgraded from interval ratio. So in most software packages, it'll accept either interval ratio or ordinal data, and it'll take care. But it is downgrading it when it does it. So this assumption of normality and even equal variance is violated. In other words, the data does not have to be normal distributed. It doesn't have to be equal variance. And what it works out, the way it works out is that this ANOVA test is more powerful. With a similar set of data, if you can make all these assumptions with a similar set of data, this one will be significant more often than this. The p-value will be smaller and allow you to reject the null hypothesis with more confidence than this one, all things being equal. Okay, that's what that means. So you want to use the more powerful test when you can, but if the assumptions are violated, you can't. Okay, so the assertion of the null hypothesis is that all samples are drawn from the same population and it's just a single population. So the alternative population, the alternative hypothesis is that each group, if it was either the high, medium, or low countries and their percentage of labor force, each group is really a different group. They're not really the same population. Okay. So when those means get closer together, it's more likely that we're going to accept the null hypothesis. In other words, if they really are from three different groups, but those groups have very similar means, then it's going to be more likely that we draw the conclusion that they are the same group. What that means is that we're defining a group by its mean and standard deviation. We're saying that similar values should have a similar mean and standard deviation. We're saying that they are the same if they have a similar mean and a similar standard deviation. Okay. All right. Now, if they have a large apparent difference, then they'll look more like this, and we're going to reject the null hypothesis and say that they are in fact from three different groups, three different populations. Okay. All right. So one of the keys here is this variance, right? We visualize variance on these. These are just the distribution by the width of this value. Okay. So we have the values. So you see how it has mu1, mu2, and mu3. These are the population distributions. These are the sample distributions. Okay, so looking at the sample distribution here, we can see that the variation of x1 goes from about here to about here. This range. Okay, the group 1. Group 2 goes from about here to here, and group 3 goes from here to here. Right. So there's some significant overlap in those three groups. The overall, if we were to consider them to be one single group, the overall variation goes from about here to about here, right? It's the overall variation in that. So the overall variation here is much greater than the overall variation here. And not only that, the variation cutoff values between group 1, group 2, and group 3, they only overlap a little bit. Okay? That's why we're considering looking at the groups. This is just a slide from your book. Okay. All right, so that's the variation that's being considered. So ANOVA kind of divides it up into those two different groups that I just talked about. The variation between groups, in other words, the overall variance, and the variation within the groups. See the variation within the groups? This is variation within the group. This is variation within the group. This is variation within the group. So in other words, the variation within this group goes from here to here, and from here to here, and here to here for group 3. So we're gonna look at the ratio of within group variation to between group variation. All right, and it compares those differences. So another way to think about this between group variability, that focuses on how the sample mean of each group differs from the total or overall mean. Okay, so these are the sample means. This is a sample mean, this is a sample mean, this is a sample mean. So what the between group variability does is it compares how different each of these sample means is from the overall mean. The overall mean would be, if we took if we drew a histogram of this entire thing, it would look kind of like that. Okay. So how much do each of these sample means differ from the overall mean in that data set? Same with these here. Okay. Again, these would look kind of like this. Kind of like that. And so how much difference would there be? Okay. Another way to think about that is that sometimes it's called the explained variation. It's the variability explained by the group structure itself. Think of 3 different groups here. The field goal percentage in a pro team versus a college team versus, my son's team if he was playing soccer anymore. Okay. So we're going to have a different average field goal percentage for those different groups, and it's that value, it's those values that we're looking at, comparing the means themselves to the overall mean. So the mean from the pro college group, the mean for the pro group, the mean from the college group, and the mean from the kids group. Okay. The within group variability measure the variation of observations in each group about the mean of that group. In other words, we're just looking at the variability within this group, the variability within this group, and the variability within this group. So if the variability within the group and the variability in the values as a whole, the means as a whole, if those values are significantly different, what it's saying is that there is a significant difference in that. Sometimes we refer to this as the unexplained variation. Okay? It's not explained by the grouping, but it's by some other factor. Okay? Yeah. And I have an example written out there. Okay. So it really is just a ratio of the between group variability and the within group variability. Okay. Between group and within group. Now there's some math that goes into calculating both of these factors, and we'll talk about that for a second just so that it kind of makes sense as to why it works. But we're not going to actually calculate out the numbers. Okay. So the first thing that we need to do is this is a formula we've used before. This is the weighted mean, right? What we're doing is multiplying every group mean value by the number of values in that group. We're adding them all up and we're dividing by the total number of values. This is the formula for weighted mean. So this XT, which they're calling in your book, they refer to as the overall mean. It's the weighted mean for each group. It's the weighted mean for all of the values using the group means and then their numbers. Okay, so that's what XT means there. It's just the weighted mean. Right? So we take that weighted mean, and what we're going to do is take each group mean and find the difference between the individual group mean and the overall weighted mean and square that difference. So we call it the sum of squares there. Okay, so it's the sum of square differences between each group and the overall mean. We're going to square them. Okay. So you can imagine well, no, you don't have to imagine. The greater the difference between each individual mean and the overall mean, the bigger this number is going to be. Okay. One reason that we call this analysis of variance is that the next formula here, which is really just a reworking of this formula, that looks a whole lot like the formula for variance, except for now, instead of talking about the individual observations, we're calculating the variance of the means about the overall mean. In other words, as these values spread apart further, the variance is going to increase. This one's going to have a higher variance or sum of squares than this one. Okay. Where was I? Right there. Yep. All right. So that is the that's the sum of squares between the groups. The last thing to do is to normalize that, just like you would with the variance value. You normalize that by the number of observations. So they call that the degree the degrees of freedom value, but it's not the actual number of observations in this case. It's the number of observations in this case is the number of groups. See what I'm saying? So the number of groups minus 1. So in this case, it would just be 3 minus 1, so it would be 2 right there. So it's truly the variance of those values, of the mean values. Okay. So that's the between group. That's the between group values. Now, I need to delete that, it looks like. Anyway, we're moving on now to the within group. Oh, just don't want to leave that up because it's kind of confusing. I tried to cover it up. All right. So that was between group. So that's the numerator. Let's go back up to here. The numerator here. Okay, now we're going to do the denominator. The denominator is the within group variability. So let's look at how we calculate that. Well, what we do is we take the variance for each group and we weight the variance for each group by the number of observations in that group. Okay, so we got the group variance and the number of observations, and we add those up. So we'll have 3 different variance values in this case, and we square each of those. We multiply them by the number of values in each of those variance values, so we're weighting them, and we add all those up, weighted by its sample size. And so, in order to calculate the average of that within group variance, we need to divide that by the within group degrees of freedom. So we need to normalize it, and that equals the total number of observations in all samples. The reason why is because we used n here is the total number of samples in each group. So if we want to truly weight it, our weight value needs to be the sum of all of the weights. Okay. So it's the sum of all of the weights divided by the number of samples. And the reason why it's not 1 here is because we already subtracted 1 here. So we subtracted 1, 2, 3 times. So k is the number of groups. And so in order to get the right number here, you take the number of observations minus k, which is the number of groups. All right. Okay, so yeah, that's that's the denominator. So this is an estimate of the within group variance. So it's the reason that we can't just take any group's variance is because we need an estimate of the overall variance. So we need to find the variance in each group and then weight them, and that's what this does. All right. So finally, we get a number, and this once we take the ratio of those two, we get a number. And the number that we get is the ratio of between group variance, and it creates a statistic that's called the F statistic. And it has a different distribution than the Z or the T, which were very similar. The F actually looks a little bit more skewed, okay, but it still has a tail, and the tail is what we're interested in. And if we look at the F distribution and we look out the F distribution, we could calculate a p-value based on that and the cutoff value. You probably won't use them too often, but on page 308 in the book, it does have the F distribution cutoff values, and you'll notice that there are two different. The way that you read that is that there's the degrees of freedom for the numerator and the degrees of freedom for the denominator, and you just find it, and then you actually get the cutoff value you'll actually get the alpha, the cutoff value, and so you would compare that. Okay, but in practice, you run it through. Most often, you just run it through software and you get a value. Okay. All right, so here's that table we talked about for the ANOVA. You can compare 3 or more independent samples. Remember, the 2-sample dependent, or the 2-sample independent was the same. Compare 2 independent random samples for difference. Okay. All right, so here's a small example. Four different values, and them working it out by hand. Basically, what they're doing here is taking each of the n is the number of observations, x bar is the average, and the s is the standard deviation. Okay. So those are all the statistics that you need to calculate. You don't actually need the raw values to calculate an ANOVA. You just need these 3 values. Okay. So we calculate. The first thing that we're going to do is calculate that weighted mean. Remember, the weighted mean is just the number, just the n times x bar, n times x bar over and over again, and then divide that by the sum of the weights. Okay, so that's the weighted mean, 28.94, or what they're calling the overall mean. Weighted mean, overall mean, mean the same thing here. Okay. All right. Then next, we're going to calculate the sum of the squared values. The between group sum of squares. The between group sum of squares is essentially the variance of these x bar values. Okay. So we're going to take each value, we're going to weight it by its sample size and square it. Okay, so we did that over and over again. And then because it's calculating the variance, we need to subtract that from the overall mean. That's that value there. And we need to also weight that accordingly. So we get a value of 227.5 for the between group sum of squares once we divide it by the degrees of freedom. In other words, by the number of groups. See how there's minus 1. There's 4 groups. Number of groups minus 1 is 3. And then we calculate that within group variability by basically taking the standard deviation, turning it back into variance by squaring it, and then weighting it by the number in each. So it's basically the weighted standard deviation. I mean, the weighted variance once we square it. Okay. So we add all those up, and to get the true weighted variance, we need to divide by the number of observations. So that's 200 minus 4. It's 200 observations. And because each one needed to be n minus 1, we say minus 4, we get a value of 10.1. And then we get the ratio, so we get a value of 22.54. The p-value that gets created from that is 0.001. So in that case, would we accept or reject the null hypothesis? 0.001 is very, very small. Is it larger or smaller than 0.05? It's much smaller than 0.05. So we can reject the null hypothesis that I forgot to actually talk about that. These numbers represent the obesity rates in each census level. So the obesity rates are, the null hypothesis would be that the obesity rates are the same in the Midwest, Northeast, South, and West. But what we're saying is that the obesity rates are not the same in the Midwest because this p-value is so low. We're rejecting the null hypothesis. Okay. Now, you may right now be thinking, wait, now this is different because we're not doing greater than or less than. We're not thinking about that. You're right. Once you start doing 3 or 4 groups, the null hypothesis is always just different. So you're saying, are these groups the same, or are they not the same? Those are the null hypothesis is, are these groups from the same population? The alternative hypothesis is, are they from different populations? So that's one of the reasons, going back to what I said earlier, that's one of the reasons why when you just compare 2 different ones, you might get an answer. So it might be that the Midwest and Northeast ones, probably not though. Well, yeah, it might be that the Northeast and the West, if you just ran it, there might be no significant difference between the Northeast and the West. And there might be a significant difference between the South and the West. Probably would be, okay? But that's a different question. And we're asking the question, are these groups likely from the same population, or are they not? And that you're going to get a different answer. Just because one group would be different from all the others in a paired t-test or in a t-test doesn't mean that the ANOVA will necessarily say that they are different. Okay. I mean, obviously, if one of them is way different enough, it will. But we're asking the question overall: are these likely to come from the same overall population as a group, rather than the individual? The question. So sometimes people do like to run both tests. Okay. And that's a way to report on how it might be different one way versus the other. Okay. So in this case, because this value is small, we're rejecting the null hypothesis that they are similar, and we're saying that there is something different. Okay. Here's a box plot of all these values, by the way. Okay, so here's the South, the Northeast, and the West. So we may, if we ran these two on the t-test, they may not be different. I don't know. Well, actually, that's right here. Sorry, I knew it was coming up, but I didn't know it was on this slide. Okay, so we do have the Northeast compared to the West. Look at the p-value there, 0.9449. That p-value is really high. It's almost 1, and so the hypothesis test there, if we were doing a t-test, would be that the Northeast and the West, there's no significant difference between those two. Their means are equal. They come from they are the same overall population, and we'd have to fail to reject that null hypothesis, and we would have that value. It looks like almost all the other ones, except for the Midwest and Northeast, it would depend on whether or not we wanted to call this a one or two tail test. If it was a one tail test, we would definitely, that's the Midwest and the Northeast. So if we had some reason to believe that the Northeast should have lower obesity rates, then we could set that as our alternative hypothesis, and we could reject the null hypothesis that they're equal and say that they are in fact two different populations. Okay. So, but if we didn't have any reason to believe and we just wanted to compare the two, then we couldn't reject the null hypothesis because that doesn't reach the 0.05 standard. All right. Okay, I'll go through this fairly quickly, and then we could be done for the day. But the Kruskal-Wallis test is the nonparametric equivalent to an ANOVA. In other words, you use it the same way you use an ANOVA test. And the null hypothesis is the same as is the alternative hypothesis, that one of the groups is significantly different. So the null hypothesis is that they are all from the same population. The math, and I won't go through the math like I did on the other one, but basically you're looking at the ranks, the mean ranks of each value. So the ranks are getting put together in a similar way. You see, we're still weighting ranks, and we're still taking those ranks and weighting those, and then coming up with a test statistic. So here's the overall test statistics. It's actually called an H statistic, and that statistic is, I don't believe it's even in the book. I don't believe that it is. But, okay, yeah, you're supposed to use the chi-square. I remember that. Okay, so to determine the p-value, there is the chi-square tables in the book. So you could use those or run them in statistical software like Python. Okay. So here's the table for the Kruskal-Wallis test. Basically, it's the same, but it has different assumptions, and it can use ordinal data, and the data does not have to be normally distributed or close to normally distributed, and the variances actually can be different between groups in order for this test to work. Okay, so here is an example of using both. We're going to use, in this one, we're going to use both the Kruskal-Wallis and the ANOVA to test. Okay, we've got these four groups. Notice again that the groups do not have to be the same size. We have different size groups. So these are homes purchased in each group, and we want to determine if the home purchase price, which is in thousands of dollars, so this is $218,000. If home purchase prices in each region of the city, are they significantly different from each other, or are they the same? We might be asking that question because we want to know, is one area, are the housing prices different? Is one area more better off than the other areas? Okay. So in order to do that, we take those values. Here's the work table. These are kind of like miniature box plots. You can see the mean and the standard deviation, or the variance of both, of all four of these categories. And you could see that there are some differences. There are overlaps, but overall, when we plug this into an ANOVA, we get a value of 0.00, which means that at least one of the four districts has a purchase price that's different from the other districts. So in other words, they're not all equal. They're not all from the same population. Okay. All right. Now, if we were to do the same thing oh, well, this is, sorry, this is just looking at each individual paired. So sometimes this is useful because we want to see, well, the south side and the central that different? No, they're not that different. Is the east and the central different? Yeah, those are very significantly different. Eastern and central are very significantly different. Okay, so that's looking at each pair of t-tests. All right, let's look at the non-parametric results. So looking at this data and looking at the mean and the standard deviation, it appears that none of these distributions are significantly skewed. Okay, however, let's say that we had some reason to believe that they were, then we would have to use a non-parametric result. And so here we've taken all of the data and we've ranked it. So in other words, this data here, 151, that has an overall rank of 1. It actually doesn't matter if you rank them from highest to lowest or lowest to highest. They rank them from lowest to highest here. So this is the lowest selling home. And this is the third, where's the second? So there's the second lowest selling home. You can see that there's actually a lot of lower selling homes in the central. And then there's a fair bit over here in the south side. Okay, the third, the sixth, the fifth, they're all on the south side. So this here is the sum of the rank. This is the weights rank. I mean the number of values in that. And then this right here is the average rank for the south side, the average rank for eastern, the average rank for central, the average rank for the north side. You see that? So that's what it's doing. It's taking the average rank for each group. Now, what was I going to say? Oh, you'll notice that there are some that have the exact same value. So there's a 13.5 here because it has the exact same value over here, 13.5. So there's two with the same value. But notice that what that means is that there's no 14. It just goes right to 15. See, 15. There's no 14s in here because it just carries on. Right. Okay, so it calculates the test statistic with all those numbers. Again, we're not gonna get too far into the math here on the ranks, but it's doing a similar thing. And so here's the test statistics that's calculated, and there's the associated p-value. And you can see that p-value, 0.001, by the way, what this means right here, it says both adjusted and non-adjusted for ties. Kruskal-Wallis, if there are too many ties, it has a problem with that. And so there's a factor to adjust for ties. So if your data has a lot of ties, that's one of the things that you need to pay attention to, but I'm not going to put that on any test or anything. It's just something to keep in mind. Okay. So anyway, the p-value is 0.001. Let's compare the p-values between these two tests. So that's 0.001. That is 0.000. So you can see that the ANOVA test was more powerful. It allowed us to reject the null hypothesis with more confidence. Now, we would have rejected them in either case. 0.001 and 0.000 both would cause us to reject the null hypothesis that they all have the same, that they're all from the same group, that their sample values are all the same. Okay? I mean, sorry, yeah, that their sale values are all the same. They're all drawn from the same sample. All right. So to follow that up, we could use the non-parametric version of the t-test to look at all the differences between the two. So in other words, this is a non-parametric version of this. Okay. So you can see 0.01 between south side and eastern, and we've got 0.0, oh, I don't need to go back and forth. So we've got 0.0128. So those values are close, but this value is a little bit higher. Same with this, 0.216 versus 0.268. So these values are more powerful. They allow us to reject the null hypothesis with more confidence, but we have to make more assumptions. We have to assume that the data is normally distributed and that the variances of the groups are similar. Okay? If we can't make those assumptions, it's better to use these values where the values are higher, and they would cause There's no example in here where they'd actually, well, actually this one right here, East or Central? Central and Easton. Easton, Central, yep. So that one right there, no, it's still 0.002. I was thinking it was 0.02. There's none here where it would matter. We would, at the 0.95 level, we would reject, accept, reject, reject, accept, reject, and we'd do the same here. Reject, accept, accept, accept. I mean, sorry, reject, reject, accept, and reject. So we do the same for each of these. But there could be an example where it's right on the edge, and so we'd have to think about whether or not we'd be safe to assume that our data was normal. We have to look back through our data. Oh, does it look like it's normal? Does it look like the variances are similar? Then we could make that assumption and go with the ANOVA. In this case, the data does look pretty normal, and it doesn't really matter for the overall answer anyway. But all right, so the last example here is looking at immigrant populations, and what we're looking at here is, are the immigrant populations in different regions similar, or are they different? In other words, are there more immigrants in the South than the West or the Northeast? So we're still looking at different areas of the country. Okay, and you can see right here that it does appear that the South has a higher immigrant population than many other areas. That's actually the growth in immigrant population, the recent growth in immigrant population. So that's what we see here. So you can see the South has a percent change, that's what I meant by growth, in immigrant population. It has the highest percent change. The other areas aren't changing as much. Okay. So if we run the analysis of variance, we get a p-value that is 0.000. So what does that tell us? Well, it tells us that we can reject the null hypothesis that these values are all similar and say that at least one of them is significantly different than the others. Okay. Same with that. Same with these values. This is the Kruskal-Wallis version, and we can again reject the null hypothesis and draw the same conclusion. Now, what's really kind of interesting is that, well, not it, I guess. What I'm trying to say is that oftentimes it is interesting to come up with and do these aggregate tests and come up with a value, but sometimes it's interesting to look at outliers. So here we've got the South, and also it seems like it's the South and East, but as you go further north, you get less, and Scranton is actually an outlier in the Northeast. So Scranton actually has a greater change in the difference in immigrant population. Why? Well, I don't know, but that would be something that would be interesting to study, or maybe why it's like the reason why I didn't point out Iowa is that in some ways there's a lot of similarities between Iowa and some of these other places in the South in terms of culture. But Scranton, Pennsylvania is largely urban. It's a Rust Belt city, and so what's making it different than some of these other areas? Anyway, so that's one of the things that's nice about coupling these analysis with an actual map and coming up with a reason or kind of describing why that might be. Okay. So the point is that these statistical measures are important tools, but they're just one tool in analyzing the data. Okay. All right. So, oh yeah, this I just had in there from before. We already reviewed chapter 10 today, so we don't need to consider this now. All right. So, what I'll do is I'm going to put up a similar homework assignment with a similar result, but I had trouble getting it to run right on my computer up here on campus. I am on campus because my internet's not fast enough to stream the video out. So I'll get that assignment up now, and then you'll have chapter 10 and chapter 11, and I'll make chapter 10 due on the end of next week, and chapter 11 due the end of week after, and then I'll keep staggering each one like that. Okay. So in each case, though, the workflow will be similar, and the format will be similar, where you identify the test to be done, and then look at the outputs that I run. For the next few weeks, there'll be Python outputs, and then there'll be some when we start doing spatial stuff that'll be ArcGIS outputs. Okay, but either way, there'll be a test statistic that we're talking about, and you'll interpret it. Okay, a test statistic and a p-value, and you'll interpret that. All right. It has been a little bit weird doing this with less feedback. I can't see any of you guys, and I feel like I get less questions, but yeah, let me know what you think. Well, you know, when you're in the classroom, you can see when somebody might look a little confused and so on. But yeah, so we can use this same format. I can share data. I can show my screen if I need to show you how to do something on the tests. I mean, on the answers to the questions and so on. So let me know if you want to meet. Like I said, I'll always be on at 10 o'clock. Starting from before class. If there's another time that you want to meet, just let me know, and I can start up one of these Skype for Business things, and we can share our screens and answer the question. So, all right.
Well, thanks for the effort, because you did a lot of shifting around.
Well, yeah, I think the biggest effort is going to be the retooling of the homework, which I was actually planning to do regardless. But we do, and my other class was a little bit more changing. But yeah, any time that you need to get in and ask me about a question. I've done this before with several other students, so it works even before the craziness happened. We can usually answer questions fairly easily through this format, and I can even do it from home if it's just if it's one or two of you. But every once in a while the call drops out from home. I tested it yesterday, calling my wife or kid in the other room and testing it out, and it wasn't as good of an experience, so that's why I came up here.
Well, terrific. Thanks for that.
All right. Well, thank you all for persevering, and keep up the good work, and don't get sick.
Thank you, Dr. Raber.
All right. Thanks, Ashley. All right. Y'all have a good day.
You too.